All right, let's get started. And maybe first what we can do is address some of the questions in the chat. I see a few are still coming through. Maddie, did that answer your, did the answer Renee and I give answer your question? Sort of. Okay. Maybe we can talk about that more in the discussion. And there is a question from Bar, and it said, what would happen if we set the viscosity of the mantle to a very low value for the beam model? Will we, in essence, only model an elastic response? Will Aspect know how to deal with that? If we set the viscosity of the surrounding value to a low value, in that case, though, it would be more viscous. Did you, Bar? Did you mean the shear modulus of the or sort of the shear modulus of the mantle? I guess the short answer is that if you basically had that model set up with the beam and the surrounding material, and they were both had very similar viscoelastic properties, so then they had basically the same reference viscosity, had the same elastic shear modulus, then yes, effectively what you would be doing is if you turn on gravity and the only difference between the materials is the density of the beam, then yes, you are effectively modeling only elastic deformation, and basically the total component of deformation associated with viscous flow is going to be very low. And so the answer is yes, it can handle that. Aspect can handle that. But what you would just see is large accumulation of stresses, but then if you're modeling, let's say, composite creep, like this, dislocation creep, is your viscosity your effective viscosity would just be very low, and almost all the deformation would be driven by the elastic response. There are probably certainly scenarios where we actually haven't tested where our formulation breaks down, but for the most part, though, at least for these incompressible viscoelastic cases, all the known benchmarks that we can think of seem to be passing well. So, yeah, so thumbs up on that end. If you want to entirely model entirely viscoelastic system, absolutely, it should work. Great. So what I'm going to do now is before we move on to the Continental Extension Cookbook, I'm going to go back to pair review quickly and show what it looks like when you have the beam, or sort of how to visualize this bending beam benchmark. I'm not sure exactly why my mouse is freezing at some cases. I think it seems to be happening mostly when I'm doing the screen share, so I'm going to try and avoid it as much as possible. But here I've loaded in solution.pvd associated with the bending beam example. And so what I'm plotting here is the beam itself. So there's all these different fields you could plot. You could plot the strain rate, you could plot pressure, you plot density, you plot the beam. And so then what I chose to plot here is the beam. And so basically the value is 1. So this is the compositional field representing the beam, and the background material is 0. And then if you hit play, okay, you're going to see this model, you're going to see the beam bend over time. So one thing I thought I would quickly do, which is really useful, in the plots I showed you, I had the time included in the model, and you can do this automatically if you load the solution.pvd. So what you can do to plot that is if you go to filters, and then you go to temporal, annotate time filter, and click that, and then click apply. You're actually going to see the model time. And so in this case, this is at 50,000 years. You can adjust things like exactly what message is printed out here and the formatting of the string associated with time. You could scale the value. So here, if I want to scale this down to be in terms of tens of thousand years rather than years, I could here type in 1. Well, it's not actually letting me type in there. Sorry about that. But you could change this value to scale 1e - 3, and then the value here would be 50e rather than 50,000. And so then oftentimes what I might do in this box is I might write in, I just do percentage 2.1f, which would give you 1 decimal point after, it would give you 1 decimal point printed out here rather than 5, and then I would scale it by 1e minus 3, and then after this I'd put KYR, and so then the value you have reading here would be 50 KYR, or 50,000 years. And then you can also do things like change the font color, change the font size, and change the font type, and then also change with these things, with these buttons right here, change exactly where those values are plotted. So let's go back. We'll move on now to continental extension unless there are any further questions associated with the bending beam benchmark. And I'll share that. Yeah. So then now we're moving from sort of a viscoelastic example to a viscoplastic example. And what we're going to be looking at is an example of a simple example of a continental extension model. So what's happening during continental extension? Effectively, you have divergent plate forces, and so indicated by the arrows here, you're pulling things apart rather than compressing. And during this process, and of course during basically any lithospheric deformation process, you have a wide range of deformation mechanisms occurring. So you're going to have a combination of brittle deformation. This would be represented by the faulting here in sort of the crust and partway into the mantle. You're going to have viscous flow dominating both in some places in the crust and ductile layers in the crust, and certainly in the lowermost mantle lithosphere. And in some places, you're going to also have elastic deformation occurring as well, associated with the fault rotation. Also here, one thing you can notice is that a common feature of continental rifts is that you have magnetism. This is because as you have advective heat transports, the lithosphere is thinning, heat is being driven up through the asthenosphere, the geothermal gradient is getting hotter, so you often have decompression melting in the asthenosphere, which then comes up and is either expressed as volcanism at the surface or sort of plutonism within the lithosphere itself. And so then, if extension occurs long enough, you might potentially then go to break up the continental plate, and then you'd have an entirely new process, which would be oceanic spreading here. Now, in this example, modeling all of this in a single model, to my knowledge, no one has actually been able to do this and actually couple all these processes properly in a lithospheric dynamics model. So then what we're going to do today is just look at a case where you have brittle and viscous deformation, you have divergent plate boundary forces, but we're only going to run the model for a short period of time, and so we're not going to take into account variations in the lithospheric asthenosphere boundary topography over time. We're basically just look at the very initial stage of continental extension of fault formation. Although I will note that a number of us are working on coupling two-phase flow and magnetism. Yuliana is going to be talking about that tomorrow, to brittle failure, and so then eventually we hope in the next couple of years we're going to be able to look at actually what happens as magma or volatiles actually move up through the lithosphere and influence the faulting patterns themselves. So how would you design a simple continental extension model? This is sort of based on this diagram. It's completely hypothetical, but it's sort of based on the existing continental extension cookbook we have in the aspect repository. So here's what I would do, and then this is sort of based on a large number of models people ran in sort of the early 2000s and sort of maybe between 2010 and 2015 to look at the effects of various properties during continental extension. So what we're going to do, I guess the key point is that we're going to drive deformation through velocity boundary conditions. In the viscoelastic bending beam example we showed you before, deformation was only driven by internal buoyancy forces. And although gravity is on in this model, is turned on in this model, the main driver of deformation is actually velocities we apply at the sides. So what we're doing here is we're saying we're going to extend the model or deform the model at a constant rate by constant velocities on either side. So here we're pulling on this side, let's say at a rate of 0.5 centimeter a year. On this side, we're pulling at a rate of 0.5 centimeter as well. And on the bottom, we're going to have inflow of material. What this does is the velocity you could set here could exactly balance the outflow on the sides. That means for however much your model extends, you're going to have an equivalent amount of material flowing in. And so that means your average surface topography is going to stay constant over time. Now that's an assumption. It may not be a correct assumption. You could have scenarios during extension where your average elevation is decreasing over time. But then for the models here, we're going to make the assumption that average topography stays constant over time, or average topography stays constant over time. At the top, we're going to have a free surface, similar which is what we had in some of the models Renee showed yesterday. And so then this is boundary stress-free, and it's allowed to deform over time in response to deformation in other parts of the model. So what about the material properties? So then in its simplest form, you could divide the lithosphere into a crust and mantle. These would be characterized by different properties. They'd have different densities. They'd have different nonlinear viscous flow laws associated with them. They might have different brittle properties, although in most cases, I and basically everyone else tend to keep the brittle properties between different materials the same. And then here, oftentimes what you need to do in basically all cases in numerical models is if you just have a flat moho between the crust and the mantle, and you start pulling, is you're going to undergo a significant amount of pure shear thinning. So basically the whole system is just going to start thinning. The crust is going to get thinner. You're not going to localize deformation. So what oftentimes people do is they incorporate some sort of heterogeneity in the model. In this case, it's a weak seed. In this case, this could be it could be a lower friction cohesion angle. It could be a different viscous flow law than the surrounding mantle. And then what that's going to do is going to basically localize deformation at this point. And what you end up seeing is conjugate shear bands coming up very quickly from this. And you basically get a very simple symmetric Horst-Grobman system due to the introduction of this weak seed. We're actually going to take a different approach in the example today, but this was up until 5 or so years ago, this was a very common approach to model this kind of system. Throughout the system, you might have you're going to have a variable temperature structure that might be defined by a classic continental geotherm. So a moho temperature for a 30 kilometer crust might be 500 C. The temperature at the base of the lithosphere might be 1200 C. And then the thermodynamic values, such as like the internal, the rate of internal heating might be different between these two things, which would give you a non-linear geotherm. It would give you a very different profile. So in the Aspect Continental Extension Cookbook, and we're actually going to do a modified version of this cookbook today, it is very similar to the diagram I showed you before. In that cookbook, what you have is you actually have a 2-layer crust. So in this case, you have upper crust, lower crust. They're defined by different densities and different viscous flow laws. But then also in the mantle here, but then in the mantle you have, it's not shown here, but you do have a weak seed. And what that leads to, this is after, I believe, 1 or 5 million years of deformation. I don't recall off the top of my head, but you basically, at this weak seed, which is introduced here, you form these sort of conjugate shear bands. This figure is showing the strain rate, so it's basically showing you the rate of deformation. Deformation localizes along that seed. In most of these regions, you're undergoing brittle deformation, although in the uppermost, or in the bottom of the upper crust, in the bottom of the upper crust, you do have some ductile deformation. But for the most part here, you have 2 brittle shear bands coming up off of this weak seed, and you develop sort of the simple Horst-Grobman system. So what we can do now is we can go back to the virtual machine, and we're going to run a modified version of this Continental Extension Cookbook, which does a bit better job at the initial, at the way to initialize deformation. So what you can do in the virtual machine, and I'll do the same steps in a second, is if you're already in a terminal, you're still going to be in session 3. And similar to the viscoelastic bending beam benchmark, what you can do is if you open the Continental Extension Cookbook, the model time by default is set to 1 million years. If you're running in release mode, and if your model, or even in debug mode, and your models are running reasonably fast, you can comfortably change this end time to 5 million years. In running on 2 processors yesterday in release mode, I was able to run this model in about 20 minutes with the model end time set to 5 million years. So then you can do that by doing leafpad, continental extension.prm, and then changing the end time, which is right at the top of the model. And then what you would do is then do MPI run, the same process as before, MPI run -MP2, or whatever number of processors you want to use, point to the aspect release binary, and then the name of the model. So then I'll give everyone like 10 seconds to sort of look at this, and then I'll go back to my virtual machine and run the same model. There's a question in the chat which says, can I run this simultaneously with the bending beam? my answer would probably be no. I mean, unless you have 6 or 8 processors and a fair amount of RAM dedicated to the virtual machine, I would advise against running these models at the same time. All right, so I will go to the back to my virtual machine. All right. So here I am I'm in the session 3 folder. What I'm actually going to do to clean things up is remove the old folder I had for the Continental Extension Cookbook, which I ran yesterday. So now then what I'm going to do is do MPI run -mp2 point to my aspect release. And then give the name of the Continental Extension Cookbook. Yep, and now we are running. So now we'll switch back to PowerPoint quickly. And that should take about maybe 20 minutes to run. So before we move on, are there any questions about this? Or did anyone have any trouble running this model? Yes, I see a number of questions. And so some of the questions are, what happens with the simple extension model if we set up the weak seed for the crust? How is the weak seed implemented? And so the answer to the first question, what would happen if we put the weak seed in the crust? The answer would be that basically it moves the height of where the conjugate shear bands initiate higher up, and so it means your Horst and Graben system would be smaller. The deeper that seed is, and so the deeper you have the sort of origin point of those conjugate shear bands, it's basically going to take a longer distance to go up to the surface of the model. So then you're going to have a wider Horst and Graben system. Meng asked, how is the weak seed implemented? In that model, it was actually, in the model I showed you on the previous slide, it was actually a change in the viscous flow law. So then within the mantle, we had another material which had the same density as the mantle, but we gave it the flow law of the lower crust, which is a weaker flow law than the mantle. And so then shear bands initiated there. Maddie asks, why are your conjugate shear bands nearly orthogonal? Good question. Yeah, and so then they're basically, yeah, and so then what happens in models with plasticity, it's sort of an issue inherent to the formulation, is that at low resolutions, you get 45-degree shear bands. And so then what that means is that, I mean, effectively, as you increase your numerical resolution, the shear bands themselves get narrower and the angle of the shear bands increases. And if you go to high enough resolution, say 100-meter grid spacing, you're going to get 60-degree shear bands in extension and 30-degree shear bands in compression. And however, we haven't finished implementing this yet, but there is a fix for this, where then if you take into account dilational effects and you do associated plasticity, you can get the correct shear band angle based on your friction, based on the friction angle you supply at any numerical resolution. So then that'll probably be implemented hopefully sometime over the next few months. We already sort of worked it out, but we just need to implement it in the viscoplastic material model. And there's a question from Udio, is there multiple weak seed scenario possible? And the answer is yes, and we're about to go through that exactly in this modified Continental Extension Cookbook. Oops, sorry. So then, the modified Continental Extension Cookbook. So what do we do? And so the model you're running, how has it changed from the existing Continental Extension Cookbook aspect? What we did is, I actually changed a number of things. I changed the lithospheric structure so that instead of having a 30-kilometer thick crust, we have a 40-kilometer thick crust. And also the geothermal gradient is slightly different. We added strain softening. So in the previous model I showed, there was no strain softening of the friction or cohesion angle. We've added that in. Rather than have a weak seed based on lithology, now we actually initiate deformation with plastic strain, or so basically which is then tied to the strain softening of the friction and cohesion angle. We changed how the free surface is advected. So we did a normal advection scheme rather than a vertical advection scheme. And I'll go into that a bit more as well. We changed the solver scheme. And I also have variable initial mesh refinement. And so then now while the model is running, let's go through all of those things. So if you want to follow along in your virtual machine, you could open the parameter file with LeafPad or XDG open, but feel free to just follow along on the screen here. So what do the global parameters look like? So then, of course, these are the standard things: dimension equal to, the start time is equal to 0. And the model I've run, I'm setting it to just 1 million years, although some of you may have changed this, to run for 5 million years. We're using years in output instead of seconds equals true. And this is something new. So because this model, we're using nonlinear viscous flow, nonlinear plasticity, we have to do global nonlinear iterations. And to do that, the scheme we're using is a single advection iterated Newton-Stokes. I'll go over the details of that a bit later, but basically what this means is that at each time step, you only do a single advection solve for the compositional fields and temperatures, but we do multiple solves for the Stokes fields. And the way this procedure works is as follows. So what you do is you start off, you do an initial solve based on a background strain rate at the very first time. Then, through that, then you have a velocity for the model. Then you go back, you update all of your material properties to account for the new velocity field, and then you calculate the solution again. And basically what you do is you iterate on that, is you keep iterating until the solution has stopped changing significantly. And then what I mean by significantly is that you actually define the value for this. So then here we're setting our nonlinear solver tolerance to 1e-4, which is actually a relatively coarse value. It's not super accurate in the larger scheme of things, but this is telling us when we can stop doing nonlinearations. So now in combination with that, I've done something actually awful for this cookbook to make sure it runs quickly. You can cap the maximum number of nonlinear iterations. Now you don't want to do this normally, or what you might normally do is set this value to something like 50 or 100. Basically just to see in a 3D model to make sure you're not doing thousands of nonlinear iterations, which if you are, then you have all sorts of other problems. Here we've capped this value to 10 to make sure we can run a reasonable amount of time. Now it turns out in this model, we only actually reach this maximum value on the first time step. After that, it converges within 1 or 2 iterations. Again, here we have a CFL value of 0.5, that's sort of an average value. The maximum time step I've set to 50,000 years, and so this is actually the time steps are always going to be equal to 50,000 years because the CFL value gives a larger time step than this. Normally for problems with plasticity, I set this value to 10 or 20,000 years, and the reason for that is having smaller time steps actually normally improves the nonlinear convergence behavior. So additional nonlinear solver options you could choose. Here we're using the Newton-Stokes solver, or sort of a permutation of it. I'm not using it in full, but you could also do single advection iterated Stokes, and that effectively choosing this option would give a very similar option to the single advection iterated Newton-Stokes schemes because of the parameters I've chosen for the Newton solver. Another option would be iterated advection and iterated Stokes, but unfortunately, we can't do this option when we're tracking fields like stresses or plastic strain. We can go into that maybe in discussion, but there's basically error checks inside Aspect which say, if you're using a feature like tracking plastic strain over time or tracking elastic stresses, you can't use this iterated advection scheme. So on your screen as the model is running, here's an example of what the screen output actually looks like at the very first time step. So the nonlinear iterations, and so what I meant by nonlinear iterations is you can actually look at what the solution is doing over time. So then here, this is the very first time step. We're doing the initial solves for everything. These values are 0 because we haven't actually set anything up yet. And so then we get these initial sort of residuals for the Newton solver. What then happens after this is and so if you look at your tolerance, and where's the tolerance here? There is no tolerance yet, but once you get to this point here, and so now we're going through all the nonlinear iterations, there it is. On iteration 1, your nonlinear residual is 1, and our value we need to reach is 1e minus 4. So we're going to keep going. Here on iteration 2, it's 0.01, so still way off. And on iteration 3, we're slowly, we're systematically decreasing this value, but we haven't reached there yet. Now, it turns out in this model, it would have taken about 50 nonlinear iterations on the first time step to reach the value of 1e minus 4, but I capped it at 10. So then the solution just continues on after that. However, in all the remaining time steps, it reaches the value of 1e minus 4 quite quickly. But then what you're seeing right here, this is the code outputting what is happening on the different nonlinear iterations. So how about the model geometry and sort of the grid spacing we're using? So the model is 200 by 100 kilometers. This is another modification of the Continental Extension Cookbook, the existing one in Aspect. The existing one is 400 by 100 kilometers. I decreased that so we could run the model more quickly and also use a slightly higher resolution. So what we're doing right here is that, we're saying, okay, here the x extent of the model is 200 kilometers wide, it's 100 kilometers deep, and we initially have 10 repetitions in the x direction and 5 repetitions in the y direction. This is setting the very initial grid spacing. And so basically now the element spacing is equal initially. And so you have 20-kilometer grid spacing. And what that allows us to do is when we do, in the next slide, I'll show you, adaptive refinement means our element spacing is always constant. In general, for lithospheric dynamics problems, you do not want to start out, or basically any problem, you normally do not want to start out and have a scenario where your elements are distorted. So you have, let's say, 40-kilometer spacing in the x direction and 20-kilometer spacing in the y direction. You almost always want to have equal size elements because otherwise it's going to distort things like the angle of your shear bands. I see there are lots of questions in the chat. One of the other organizers, should I stop to answer some of these, or is it okay to keep going?
It's okay to keep going.
Okay, I just saw 11 new questions in the chat, so I don't know if I need to stop. Okay, so we'll keep going. So then what we're actually going to do in this model is use the adaptive mesh refinement features of Aspect to give us a higher resolution in the upper half of the model versus the lower half of the model. So what we do is we set the initial global refinement value equal to 2. So based on the x and y repetitions, the initial grid spacing was 20 kilometers. Once we do 2 global refinements, this means the spacing in both x and y direction is then 5 kilometers. Then what we're going to do is say, okay, I want to look at deformation processes in the upper crust. I'm primarily concerned with faulting in the upper crust, and so then for that reason, I don't necessarily care as much what's happening in the mantle in the deeper part of the model initially. So I'm going to use a higher resolution in the upper half of the model. To do that, we're going to do an initial adaptive refinement. We're going to set this value equal to 1. And what we're going to use is a strategy called minimum refinement function. So then we go into this subsection, minimum refinement function. We set the coordinate system, which is Cartesian. The variable names are x and y. And what I'm going to say is if the height of the model is greater than or equal to 50 kilometers, so that's halfway up, and I'm between horizontal positions of 40 kilometers and 160 kilometers and 60 kilometers. And so then we now have a 120 kilometer wide high resolution region above a height of 50 kilometers. Then we do one more refinement. And so then, so in that case, then we go to refinement value of 3. So then the grid spacing is 2.5. If this condition is not met, basically outside this region, then the refinement value is equal to 2, which is equivalent to the initial global refinement value, so the spacing stays at 5. So, solver settings. This is a bit tricky, and I think I'm going to leave most of the discussion of this, or I'm going to leave most of the, if people would like to discuss this, we should save it for the discussion section afterwards, because it's fairly involved. What I did here is I used the Newton's, the Newton solver to handle the nonlinear system of equations. And so then here is the subsection, the solver parameters. And in the Stokes solver parameters, what I'm doing is I'm using the block AMG method for the linear solver. This is the default value, so you would actually not need to specify this. The GMG solver is actually going to be, the block GMG is actually going to be much faster, but we can't currently use it with the free surface. This is sort of a feature in development right now. So for this problem, we're going to use the block AMG, which again is the default. And then there's also a parameter called number of cheap Stokes solver steps. I'm not going to go in detail about what this actually means. It's just a bit too complicated for the scope of this tutorial. But for problems with plasticity, it's often most efficient to set this value equal to 0. You could try setting this to 0 or 200 and seeing how it affects them, the runtime for a small 2D model or something like that. But in most cases, I found setting this value to 0 with the AMG solver is most efficient. So now with the Noon solver, it's actually a combination. It's what the Noon solver actually allows you to do is you oftentimes start out doing standard Picard iterations, which is the default nonlinear solver in aspect, if you're not using the nonlinear solver, and then in combination doing, then using the Noon method to solve the nonlinear problem. We actually, with the settings I have here, I actually never switch on the Noon solver. I only basically do Picard iterations with the Noon solver, and that's implemented in the following way. So the set nonlinear Noon solver switch tolerance is equal to 1e minus 4, which is the same value as our global nonlinear tolerance. So then what this would mean is that when we're initially doing Picard iterations, we're only going to switch over to the Noon solver, the actual Noon solver, when we reach a value of 1e minus 4. But because our global nonlinear solver tolerance is also equal to 1 minus 4, we actually never switch the Noon. We actually never switch the Noon solver on. Also, I've set the max pre-Noon nonlinear iterations equal to 10 as well, which is consistent with the maximum number of nonlinear iterations we specified in the global parameters section. Now, the reason for doing this is that, in short, the Picard method in the Noon solver is basically an improvement or the standard Picard method in aspect. And then eventually, I believe Menno is working on transferring that method over to have being the default in aspect. But oftentimes, if I want, I just use the Picard method available through the Noon solver interface using this sort of scheme where then I match the nonlinear solver tolerance here with the global one and the maximum number of pre-Noon nonlinear iterations equal to 10. If you want to actually use the more advanced options in the Noon solver and actually use, sort of the main features of the Noon solver itself, I would suggest reading Menno and Wolfgang and co-authors' papers on this. Then also there's quite a bit of information on this in the manual, and then there's also a number of benchmarks which show how to use the Noon solver. So the velocity boundary condition. So then how are we actually driving deformation on our model? What we're doing is the total extension rate is half a centimeter a year, and we're doing this by prescribing an outward velocity on the left and right walls of 0.25 centimeters per year. So we're doing this in the boundary velocity model. And so what we're doing is we're prescribing functions on the left to right and bottom walls. So we're going to say set prescribed velocity boundary indicators is equal to left x function, right x function, and then bottom y function. What this means is that when we prescribe a function down here, by putting this x value right here or this y value right here, the function only applies to these specific components. So this means, for example, I'll actually go through the function expression first. So what we're doing is we have our variable names x and y, then I'm actually introducing some constants. So I'm saying the velocity is equal to basically 0.25 centimeters per year. In this case, I'm doing in terms of meters per year. The center of the model it has a horizontal position of 100 kilometers. The total width is equal to 200 kilometers, and the depth is equal to 100 kilometers. So then these correspond to the geometry value, the model, or the sort of the overall geometry of the model. And then the function expression for the x components and the y components is this. We're saying if x is less than the center of the model, then it's going to have, or the velocity is going to be negative v. So it's going to be negative 0.025. So on the left wall, since since we're to the left of this point C, then the value is going to be negative 0.0025 or negative 0.25 centimeters per year. So we're pulling to the left on the left wall. On the right, the value is going to be 0.025 centimeters per year. And so we're on the right wall, we're pulling to the right. So now we have divergent boundary conditions. For the y value on the bottom wall, well, which are only applying to the bottom wall, this equation right here basically exactly balances the outflow with the inflow. So, so then the vertical velocity you get from this equation right here, or the velocity you get from this equation, which is going to be applied to the y value, and so then if we had x, y, z, we need to specify 3 equations right here. But the value you get here is going to basically exactly balance the outflow. So the average surface topography is going to stay constant. So what we've done here by saying left x colon equals function, or left colon x function, is this means only this part of the equation is applied here, and the y value is free. So although we have applied through a function of constant outflow on the left wall and the right wall, the y value is unconstrained. So basically, we're not fixing the y value to this component right here. The y value is determined by the solution. And the same thing on the bottom. The x value, or this x function, or the function right here for the horizontal velocity, is not applied on the bottom wall. It only gets this vertical velocity right there. And so we have constant boundary conditions over time, constant outflow, constant inflow, and average surface topography stays constant through time. How about the initial composition? So then here it's a bit more complicated than the bending beam benchmark. We're going to have 5 compositional fields. The first 2 fields are not rock type. They're components, or they're fields associated with the accumulation of plastic strain. So the second one is the plastic strain, and we're actually going to provide an initial value for this to localize deformation. This field called non-initial plastic strain, it's basically the same as the plastic strain field, except it has the initial values associated with the plastic strain removed, but it also tracks deformation over time associated with plastic strain. I'll show you why that's useful a little bit later. Then, so these are not rock types, and so then these are not included in the volume fraction computation. So they don't affect the material properties themselves, except for when you use these values to actually modify the plastics, or the friction and cohesion through strain weakening. But they're not lithologies, and they're not included in the volume fraction computation. So then we have 3 lithologies. We have the upper crust, we have the lower crust, and the mantle lithosphere. And all of these are going to be given different material properties in the material model section. So how do we prescribe the initial position and values of these fields? We're going to do this through a function again. So here we're in the initial composition model. We're going to use functions to describe these 5 fields. And again, it's very similar to before. We have the variable names x and y, which correspond to the spatial dimensions. The value of the non-initial plastic strain is going to be 0. And then for each field that is separated by a semicolon, I'm using this backslash to go to a new line each time just for readability. The initial plastic strain field, which is actually used for the strain weakening, what we're going to do is we're going to say between horizontal positions of 50 kilometers and less than 150 kilometers, and if you're greater than a value or than a height of 50 kilometers, the value is going to be randomized between 0.5 and 1.5, so that every point in the model where this function is basically executed, the value of the initial plastic strain is going to be some random value between 0.5 and 1.5. And I'll show you again why that's useful later. Then to define the upper crust, lower crust, and mantle lithosphere, we're saying the upper crust has a thickness of 20 kilometers, or is 20 kilometers deep. So then in terms of height, we're saying the upper crust is present, has a value of 1 if you have a height greater than 8 kilometers. For the lower crust, we're saying that has a value of 1 between a height of 80 kilometers and a height of 60 kilometers. So then that means the moho is 40 kilometers deep, or has a height of 60 kilometers. And then the mantle lithosphere is present beneath 60 kilometers depth and above or equal to at the base of the model. So what does this look like? If you plot these fields in pair view, what does this look like? For the initial density structure, and again, this is both a function of the lithology, and so the reference density we give these fields, and also the temperature, of course. Here's what it looks like. So here you have the upper crust, and the average density, the reference density of the upper crust is 2,800. The reference density of the lower crust is 2,900, and the reference density of the mantle is 3,300. But of course, these values are modified by the temperature, so that's why it's not constant through here. But this does allow you to clearly see where the different lithologies are located based on the function we used. Also, what you can see here is I plotted the initial mesh. And so then remember, we refined from 5 kilometer spacing here to 2.5 kilometer spacing between x equals 40 kilometers, x equals 160 kilometers, and above a height of 50 kilometers. So here you can clearly see the effect of the mesh refinement where things are more well resolved than here. So, oh, I'm sorry, this is not the initial density structure. This is the initial plastic strain right here, but that's plotted right here. So remember, we randomized these values. So what you're looking at right here is basically random values between 0.5 and 1.5. And what you can see here is you, as expected, you have this random distribution of values. What this is going to do is, because the friction and cohesion are modified by these values, so then they're reduced linearly between 0.5 and 1.5, and we'll go into that, how that's done a bit later. But that basically means you have random zones of brittle weakness in here, and that's going to help you localize deformation initially. So, temperature boundary conditions. This is probably the most complicated part of the model, actually. So then we're using the boundary temperature model. So we're saying the fixed temperature boundary indicators are going to be the bottom and the top. The top is always going to be 273. The bottom is going to be the value given by the initial temperature. And so then here we're actually not giving values. We're actually not manually setting the values. What we're saying here is that these fixed temperature boundary indicators are going to be equal to the initial temperature, which we're going to calculate in the next section. So how do we calculate these initial temperature conditions? We're actually going to use a series of equations which are characteristic of a continental geotherm. I'm not going to go into the details here, simply for the sake of time. We can go into this later in the discussion, but basically what you have is 3 equations which describe the temperature. And so your unknowns are the temperature at the top, the surface heat flow, the radiogenic heating, depth, and the thermal conductivity. And if you give enough values, if you basically prescribe enough initial values, say you prescribe, what we're doing here is giving the value initial surface heat flow, we know the heat production each layer, we know the thermal conductivity of each layer, we can systematically go from the upper crust to the lower crust of the mantle and calculate what the geotherm looks like. These are the values we initially prescribed. I had to solve for these values using these equations ahead of time. And so then when you're actually prescribing this an aspect, here are all the constants we have associated with the continental geotherm equations. Some of these we knew in advance. We basically set those as our knowns, and then we had to solve the other ones using the 3 equations I showed for below. But here what we're doing is we have this equation for temperature, and what we're doing is in each layer, and so we have less than 20 kilometers is the upper crust, between 20 and 40 kilometers is the lower crust, and beneath 40 kilometers depth, it's the mantle. We're using the constants associated with each layer to solve for the temperature. And so then that's how that's done. Now I realize I'm going through this very quickly, but I'm happy to show people how to set this up in a Python script or answer more questions about this later on during the discussion or in a separate one-on-one session. The heating model, so then we have radiogenic heating, which we actually use to set up the initial temperature conditions. We have to have these values consistent with the values we use in the initial geotherm. And so then I use the value of 1e minus 6 for the upper crust, a value of 0.25e minus 6 for the lower crust, and 0 for the mantle, 0 for the background. And then these 2 values right here represent the non-initial plastic strain and the plastic strain. So way to specify them, but they're not actually used. But the important thing to note is the values specified here need to be consistent with the initial temperature model used and the constants you use there to drive that initial temperature field. So this is what the initial temperature structure looks like. And so then rather than being a linear geotherm, what we actually have here, so this is at a depth of this right here is at the surface of the model. This is a line plotted straight through the center of the model from the top to the bottom. So this would be at the surface. We have a value of 273 C. Once you get to 20 kilometers depth, you can actually see the shape of this curve changing. That's because the value of the radiogenic heating in the lower crust. And again, once you get to a depth of 40 kilometers, let's see if I can get my mouse there. Once you get to a depth of 40 kilometers, the shape of the curve changes again because there's no radiogenic heating in the mantle. But this is sort of a very standard characteristic conductive geotherm. And of course, all of this is going to be consistent with the initial material properties we give it, like the thermal conductivity. So then this thermal conductivity or this temperature profile is in steady state. So then if you didn't apply velocity boundary condition model and you just let it stay there and you basically just let the model sit, this temperature profile would remain in place and it wouldn't vary through time. The last section to go through is the material model, and then we can actually start looking at the model results. So then this is sort of the heart of the viscoplastic material model, or sorry, it's sort of the heart of the model, and we're using the viscoplastic material model, which combines nonlinear viscous flow with plasticity, and then also there's the option to add elasticity, but we're not going to go through that specifically in this tutorial. So what are some of the values we're looking at? Here we're looking at the reference temperature, which is equal to 273 degrees Kelvin. That's going to be used in the equation to calculate, that's going to be used to calculate the total density, including the, because basically you have your reference density and then the total density is modified by the temperature and the thermal expansion. The reference viscosity, we went into that earlier, or not earlier, but yesterday with Renee and myself. And this is basically, it's not actually modifying the material properties themselves. It's basically modifying the values in the linear system of equations for the Stokes system. And as a rule of thumb, just set this between somewhere as an average value in between your minimum and maximum viscosity. So here we're limiting the viscosity between 118 and 126. And as a general rule of thumb, I generally set it to some average value in between there. But you can also test to see how changing this value is going to affect the sort of speed of the model run. But in general, using an average, something like an average value like 122 between these two values is roughly the right thing to use. So we also, to help stabilize the solution, we also have a minimum strain rate. And so then this basically, a value of 1 e minus 20, this is a very slow deformation rate, but it basically prevents the model from having strain rates which approach 0. And then on the very first nonlinearization of the first time step, we need to supply a reference strain rate. And this, I believe this value should be consistent, roughly equivalent to the boundary conditions we've supplied. So thermodynamic values. Here, the thermal conductivity is constant. It's the same as the values we use in our initial temperature profile. The thermal expansivity is constant. The heat capacity is constant. Rather than using thermal diffusivities, we're using, to basically get at the thermal conductivity, we're directly specifying the thermal conductivities. And in order to do that, you need to set a parameter set define thermal conductivities equals true. The only thing which is changing here between models is the density. So here, this is the background material, which is equivalent to the mantle 3300. I'm setting values of 1 here for the non-initial plastic strain and the plastic strain because they're not actually used in the model. So this is kind of a reminder to myself that these values don't mean anything in the grand scheme of things. They're basically, these represent fields which are being used to track not a lithology, but a property which modifies a lithology. So these values don't actually matter. But I like you setting it to like 1 or 1,000 or something characteristic, which remind me that they're not lithologies. Then values for the lower crust, the upper crust, the lower crust, and the mantle right here. The viscosity averaging. So then we need to average because at every point of the model, after you start sort of advecting things, the values of the compositional fields are not going to always be 1, and especially at the interfaces, you're going to have some overlap between the compositional field values, which means we need to average the material properties between lithologies in that scenario. So rather than using a maximum composition value, which we use for the bending beam model, we're going to use a harmonic averaging scheme. And this gives you a much smoother value. It basically smooths the solution out, and this is going to help with the nonlinear convergence behavior over time. The disadvantage to this is you tend to get less sharp interfaces in between different lithologies over time. So how about the viscous flow component? And I think we'll probably need to take a break in a few minutes and then continue after the break. But so rather than doing a composite nonlinear viscous flow, here we're only going to look at dislocation creep. So typically, if you're looking at deformation in the uppermost mantle, you want to do a composite between diffusion and dislocation. In the lithosphere, depending on what problem you're looking at, it's normally okay to model dislocation creep. If you want to look at, say, grain size evolution in ductile shear zones, then you, of course, need to do a composite between diffusion and dislocation creep, and your problem gets much more difficult. But for the purposes of this example and many lithospheric dynamic models, dislocation creep is going to be just fine. So again, if you look at the equations, if we revisit the equations for nonlinear viscous flow, here we have the viscous stress is equal to all these terms. So you have the pre-exponential value, you have the exponent n, you have the strain rate, you have grain size if you're doing diffusion. If you're doing diffusion creep, here we're only doing dislocation creep, so the grain size does not play any role. It's basically removed from the equations. We have the activation energy, pressure, volume, gas constant, and T again. And then here's the equivalent viscosity, and here's the equivalent equation for the viscosity, I, E. But here what we're doing is actually the following. Oh, and no, I actually realized I may have made a slight mistake in the, that's interesting. I may have made a slight mistake either putting these values here or elsewhere. This value right here should be, I believe these might be slightly reordered. So then, but basically what here was we're providing these different values. Is we're doing this initial value right here is the pre-exponential factor A. This value right here is the exponent n. The activation, and this is the activation energy E right here, and this is the activation volume right here, 18E minus 6. So I may have actually misordered these slightly when I redid this problem. So then I'll go back and double check that. But if we did, I'll update the parameter file. So here then again, these values were derived from specific papers. For the upper crust, we use wet quartzite. For the lower crust, we use wet anorthite. And for the mantle and background, we used dry olivine. And the non-lithologies, it doesn't matter what value you set them to, although I think I may have slightly done an incorrect ordering here. So the last part for plasticity, E, what you would actually do is here we're actually setting parameters for the brittle yielding. So here we're setting the angles of internal friction equal to 30. We're setting the cohesions, initial cohesions equal to 20E6. But what we're doing then is we're going to weaken these values as a function of plastic strain. And again, so what that is saying right here is the friction and cohesion, they're going to linearly be reduced as a function of the plastic strain. And you'll recall our initial plastic strain was randomized between values of 0.5 and 1.5. So we're doing that. And so what we're saying right here, if our initial randomized values are between 0.5 and 1.5, then we're going to start our plasticity strain weakening intervals between 0.5 and 1.5. So it basically matches our initial randomized value. And we're weakening, between these two values, we're weakening the cohesion and friction by a factor of 4, so 0.25. Now there's also the option to do other types of weakening. So you could weaken based on the total strain, you could do viscous strain weakening. Here, we're only doing plastic weakening, so weakening of the friction and cohesion as a function of the plastic strain only. And that's basically set by this keyword, plastic weakening with plastic strain only. If you look at the aspect parameters, or if you go to parameters.prm file, you can see the different options for the strain weakening mechanism. And sort of the ideas of how to do strain weakening and plasticity in general in aspect, you can see that in Ann's paper from 2018. And a recent paper Ann and I published just this year, which uses randomized plastic strain and strain weakening to localize deformation. Fine. But here what we're looking at, and then we'll take a break in just a few minutes, is the initial deformation field at time step 0 after you've done a single, basically the first series of solves. And what this is showing is plastic yielding. And so what you have here is you have areas where you're undergoing brittle deformation in the upper crust, the lower crust, and the mantle lithosphere. And so then these blue areas represent basically ductile areas of the crust. And you have non-brittle deformation or ductile deformation in these areas because basically the temperature is high enough, and based on what flow law you're using, you are no longer exceeding the yield stress in these regions. And this is consistent with a wide range of geological observations. Most of the time you see, during continental extension, you see faults in the upper crust gradating into ductile shear zones at the base. And there's also strong evidence for ductile shear zones likely in the lower crust as well, and potentially in the mantle as well, though it's harder to find observations. So again, if you look at the strain rate invariance of the rate of deformation inside the model at time step 0, what you're seeing is basically kind of a randomized, it looks fairly randomized. And so red means you have a high strain rate, blue means you have a low strain rate. And so what you can see is this is sort of reflective of that initial plastic strain field, in that what you're seeing is basically you have shear zones, brittle shear zones trying to form using that initial randomized plastic strain field, which then reduces the friction cohesion. But but because of this randomized distribution, you haven't formed a very regular set of faults yet. It's going to do that as we progress through time, but for now, it's basically the strain rate field looks extremely randomized, and you haven't localized on discrete structures yet. However, if you run the model, keep running the model to 1 million years, what you end up seeing with the strain rate is suddenly you've localized on very specific faults. Here, you have one fault on the side, so you have a high strain rate here. It looks like you have another fault here. You have another fault here, maybe another fault there and one there, lower orders of magnitude deformation. But what you can see at the surface is you're actually deforming. So actually, you're forming fault scarps associated with these faults. So they've been stable in place for quite a while. So then here, you can see quite a bit of topography here, less topography there, and less topography there. But then, if you look at the non-initial plastic strain, which tracks how much plastic strain is accumulated through time, minus the initial value, so then this doesn't contain that initial randomization, is what you see right here is you can see deformation, brittle deformation accumulating along these faults. So here you have this major border bounding fault. There's actually a break right here and right here associated with the ductile shear zones. Here you have other faults there, you have other faults coming off there, and then multiple other faults dipping in this direction. So this would be sort of the initial stages of continental extension where you form faults. So I think at that point, it's probably time to take a break. It looks like there's a bunch of questions in the chat. Should would it be worth going through some of those, Anne or Renee or anyone else? Or should we take a break at this point?
I think most of the questions are answered. We're just discussing whether, so somebody asked whether you can set a different flow law, so diffusion, dislocation, or composite per composition, and because sometimes that is necessary. But yeah, we're saying that you cannot select the flow law per composition, but you can tweak the parameters of diffusion and dislocation to make one or the other dominant per composition.
Exactly. Yep, exactly. That's the way to do it. So you could give like the pre-exponent a value of like 1e minus 50 and n equals to 1 or something like that. And that means it's gonna, for dislocation creep, then it would only, if you do that for dislocation creep, then it would only use the diffusion creep values for the composite effectively. But yeah, so then I think I don't know if I just did this on the slide or on the parameter file itself. I may have messed up the ordering between the background material and the two compositional fields. So what I'll do, it doesn't look like it actually affected the solution, which is remarkable. But then what I'll do during the break is double check to see if I slightly misordered things in that one section, and then I'll show the updated parameter file on how you do that. That was sort of a lucky guess.
John, there's one last question asking, could you elaborate on the 6 values used for the densities?
Yes. And I think that is probably where yes, okay, no, the densities were set correctly. So what this is saying, oh, sorry, let me share my screen quickly again. So here, the density is 3,300. That's going to represent the background material. Here are these values of 1, and this is for the non-initial plastic strain and the plastic strain. And so then these values actually don't matter, right? And so then these are for basically fields which are just tracking the strain, which modify the lithologies, but they're not lithologies themselves. So we could set these values to anything we want in theory. I don't think you want to set them to a negative number because that could potentially lead to some weird issue somewhere in the code. But typically I set these things to some characteristic value like 1, just to remind myself these values are not lithologies, but they're associated with the plastic strain in this case. And then here we'd have the values for the upper crust, the lower crust, and the mantle itself.
And I think the key point that you made is that these compositional fields are sometimes used to track actual compositions and sometimes to track other quantities like strains and stresses. And in this case, the values reflect what they do, right?
Yeah.
So why do you not have to, why can't you set it to 0, for example?
I think you probably couldn't set it to 0. I don't know if for some reason, it's because what it actually does is, so then you might go through in the material model, you might actually go through and calculate a density with something, but then, that density might be, it won't be used in the volume fraction computation. But for example, like with the viscous flow laws, you don't, even if you have this parameter associated with, like a viscous flow law parameter associated with the plastic strain, you still calculate the viscosity first. And then later it's removed from the volume fraction it's not included in the volume fraction computation. And so then if you have a real world value of density or something for the viscous flow law for fields associated with plastic strain, you could lead to like, taking the law, like dividing by a negative number or something like that. And even though those values aren't used in the volume calculation, it could cause the code to crash. So I tend not to do anything too exotic when I'm setting values for the plastic strain and non-initial plastic strain or the elastic stress tensors. I basically just give them values which remind me they are not lithologies, and they're just tracking other specific fields. Any other questions before we take a break? Or Wolfgang, did you want to add something to that?
No, I think I'm just looking through the chat, and I think most of the questions there seem to be answered.
Okay. Well, then let's take a break until a 15-minute break. And so that would be until, let's say, 15 minutes from now, or then 45 minutes from now in India. So that would be, in terms of, I guess that would be Pacific time, that would be approximately 9:27. And I will look through the viscous flow law parameters to see if some of those values got set properly. All right. See you in 15 minutes.